Okay, so let's talk exponential growth. So I'm going to start here. Let's do I want to do about a 10-minute review on what you've been doing for the last couple weeks. All right, and so can somebody compare and contrast these two graphs? Without me graphing them, just by looking at the bases, what do we know about the bases? One of them's a fraction. What does that have to do with it, Amadeus? What does it change? It changes the way that the points are. Matthew?
So the 2x goes like this way, so 1/2 goes this way.
Okay, that's what I was looking for. So Matthew's saying 2 to the x is increasing, or has growth, and 1/2 is decreasing, or has decay. So there's one more thing. Okay, so that's a contrast. Can anybody give me something that is a comparison between the two?
They have the same numbers.
What do you mean by that? Sebastian says they have the same numbers.
There's some different sides of the line.
Okay, on a different side of the y, so I would use reflection over the y-axis. Leif, do you want to add? They both start at 0, 1. It's almost like our parent function, and I really want to concentrate on that today. They both start at 0, 1. I should have, let me do this. I should have put it in there. So 2 to the 0 is 1, and 1/2 to the 0 is also going to be 1. So we almost call that's our reference point. That's our parent graph, and that's what we're concentrating on, is what the graph looks like before any transformations, because that's what we did last week. So we start at 0, 1 for both of them. When I increase on the x-axis on this one, 2 to the 1 equals 2. So if I go over 1, I'm going to go up 2. And if I go in the negative direction, 2 to the negative 1 is 1/2. So each time I go in the negative direction, I'm going to get smaller and smaller and smaller. So there's that graph. Now, inversely, if I put a 1 in for x, I'm going to get 1/2. So over 1, 1/2, over 2, 1/4, over 3, 1/8. And if I go in the negative direction, 1/2 is going to turn into positive 2. So if I go back 1, it's going to turn into positive 2. And so in essence, if you look at these two tables have the exact same numbers. They're just reversed, or they're just on the other side of the y-axis. So that's super important to know, and that's where we're going to go from here. All right, so I threw these in here last second because I wanted to explain to you that you've been making these transformations all along. So what transformation is occurring? First of all, our parent graph is x squared. Y equals x squared. So what's happening to this function, the parent function? The parent function would be, let's put it in red. Y equals x squared is going to be here over 1. If I square 1, I get 1. If I square 2, I get 4. 1, 2, 3, 4. So there's our parent function. So I heard somebody say, from Amadeus, what is happening to this parent function? It's going in the positive direction by 2, so we would change it by saying, we would apply this transformation. So what's happening in the second graph? It's also over 2, but now it's also up 3. So it will be x minus 2 squared plus 3. Thank you. Caitlin. Cast testing. All right, let's look at another one. What about the one on the left? It's going to the left 3, so x plus 3, and going down 1, 2, 3, 4. Sorry, going down 4. What about the last one? It's stretching as well. I believe it's the same transformation, right? It's translated to the left. So it's translated x plus 3 squared and down 4. But instead of our parent graph being 1, 1 and 2, 4, it's stretched by 2, guys. So instead of going over 1, up 1, it's going, oh, sorry, no, it's a 3, right? Over 1, up, 1, 2, 3. Let's make sure we're right. So the second one should be 2 instead of 4. It should be 12. If it's normally 2, 4, and we're multiplying it by 3, it should be 2, 12. Let's see. Over 2, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like I'm absolutely right. 2, 12. So this would be a stretch of 3. Not super important that you remember that right now, but I want you to realize you've done it over and over again. Bless you. You've also done it with many other different functions. What about this one? Parent function of this one. Remember this? Y equals 1 over x. So how am I changing this one? Over 4, right? So where would that, how would I do that? How would I would put that minus 4 with my x, right? Remember that? My transformation to the right goes with the x. And then what do I do about it coming down 1? It's a minus 1. My function's going to be here. So now I'm going to stretch it. So instead of being a 1, 1, I'm going to go over 1, down 1, 2, 3. Down 1, over 3. Wrong spot. That's a negative. 1, 2, 3. 1, 2, 3. Remember these fun guys? 1, 2, 3. 1, 2, 3. So what would I do with that 3? Where would that go? It goes out in front of it. Remember that function? So you've already been doing this over and over again. Matthew, paying attention up here. So when I move to the right and the left, that transformation goes with x. When I move up and down, that transformation goes on the outside. A stretch always goes in front, right? With everyone we've been doing. Jay, sit up, please. Okay, so let's do this one now. Yes. Nope. It's not there for looks. Actually, what this function really looks like is this. But we pull a 3 out and say that's its stretch. Make sense? Okay. So this one, you've done these already. Normally, our parent function, sorry, let's do this in a different color. Normally, our parent function would be right here, right? Have a horizontal asymptote of y equals 0, and it would be start at 0, 1. Then if I have a base of 2, that's what I'm going off of. And then if I put 1 in, 2 to the 1 is 2. 2 to the negative 1 is a half. So there's my parent function. So the first thing I ask myself is, how has this function transformed? The easiest thing to look at is how the asymptote has changed. So the asymptote is no longer here. My function's not skimming at y equals 0. My function's now skimming up 2. So up 2 is going to be a plus 2. Next thing I'm going to look at, normally my reference points, or where my 0, 1 is, because that's what always happens with every parent graph for every base. It's always at 0, 1. So that's the next thing I'm concentrating on. That's no longer occurring anymore. That's been shifted over 1, 2, 3. So that shift over 3 changes my h to x plus 3. That's how the transformation that's going horizontal, left to right, goes with the x. Finally, I had a base of 2. That doesn't change with exponential functions. I just need to find my stretch. My stretch is normally at 0, 1. But this one doesn't stop at 1. It goes up to 1, 2, 3, 4. So I have a stretch of 4. All right, so we're going to practice this together with whiteboards. Okay? Questions from anybody so far? So what's my first thing I'm going to look at? The parent graph, and how I said start with the horizontal asymptote. That's where you want to start. Okay? How did it shift up and down, and then how did it shift left and right? It's almost like working backwards. What's my horizontal shift, then my vertical shift, then my stretch. So here's another one. The first thing I told you to start with was the horizontal asymptote. So the horizontal asymptote dropped down 1. So I say k must be negative 1. Then I look at how far it shifted on the x-axis. That reference point shifted over 4. So a shift up to the right 4 is x minus 4. I know the base is 2. That stays the same. Now I just need to figure out, this negative 1 is kind of funky over here. Now I just need to figure out how much it's stretched. Instead of being 0, 1, I now have 0, 1, 2, 3. So I have a stretch of 3. Another one?
Yes.
Okay. Okay, try that one. Now I have a half. That's the same thing as a 2, base of 2, only it's falling instead of growing, right? It's decaying. It's decreasing instead of increasing. So do that one on your whiteboards, please. Okay, let's look at this one. What am I going to start with? Decay. So it's skimming right here. It's never going to get smaller than this. So it actually went up only 1. All right? Went up 1. Now I have to look at how it shifted on the x-axis. That reference point is over 3. So that means the 1/2 must be x minus 3. And now I'm just looking at my shift, my stretch. Instead of being 0, 1 here, it's it's up 2. So it's stretched by 2. One more? I like it. I like hearing the O's. Show me that one. Okay, so I'm going to start with my asymptote. My asymptote is dropped down 2. So we've got a -2. Then we're over 1, 2, 3, 4, 5. My reference point's over 5. So 1/2 is being taken to the x. What did I say, 5? But it's going to be plus 5 because it's always the opposite, right? Because if I set x plus 5 equal to 0, what? You don't think it's 1? Really? I think it's 1. This is why, Jonathan. Check this out. 0, 1, up 1. So my stretch is just 1, or we don't have to put anything in front of that. Okay. If I were, Jonathan, if I were to put in a -1, I would get 2. Right? Okay. So if I put in, okay, Jonathan, look at this one. So here are our numbers that we use. If it's growing or increasing, my magic numbers are 0, 1, and then the next one is when I square, when I take 2 to the first power, I get 2. Matthew. So on this one, over here, it's just on the other side. It's always 0, 1, and then if I went in the negative direction, I'm also going to get 2. Do you agree with that? In the negative direction, I'm going to get 2? Yeah. So now let's go back to the graph we were using right now, okay? Because these are my parent graphs. Right here. Last one we saw is this one. Okay, so that magic number is going to be 0, 1, and then if I go in the negative direction 1, I should get 2. And that's what I get. So there is no stretch. Does that make sense? Okay, so the first one's going to be 2 to the 0, which is 1. The second one's going to be 2 to the 1, which is 2. The next one's going to be 2 to the 2, which is 4, right? So 0, 1, over 1, up 2, over 2, up 1, 2, 3, 4. You convinced? Are you good? Awesome. I'm glad you asked. And then it's hot again in here. Okay, so I think that's enough review on our transformations and our parent graphs. Now let's talk about growth. All right, so there were 300 emoji when Apple announced it was increasing this number by 10%. What if Apple released 10% more each month? What would the first 3 months look like? Talk with your table partners. Tell me how many emojis we'd have in the 3rd month. Go. So some of the questions that I got, which were great questions, is it just 10% each time, which would be 300, then 330, then 360, then 390. But what's happening when those emojis are increasing? It's still 10%. When I have 330, I'm now going to add 33, which is 10%, right? So I should have 330 the first time, 363 the second time, 399.30 the 3rd time. Can we be a little forgiving for just the sake of trying to find something that relates to what we know? Okay, thank you. All right. let's talk about what we were doing in our head, because that's what's super important about this. Okay? So what I'm doing in my head is I'm taking the 300, right? And I'm saying, okay, so 100% of 300 is 300. And I know that 10% of 300 is 30, because you guys just moved the decimal place over, correct? You guys did a good job of doing that in your head. So 10% of 300 is 30, and you just added them in your head, correct? You were all pretty much able to do that. Here's another way you could look at it. I'm going to cut out a step. Aren't I really taking 100% and adding 10% to it? I'm taking the whole 300. Matthew, I need you to, Michael, I need you to pick up your head. So I'm taking the whole 100% and 10%, which is my 30. So isn't that kind of just like distribution? 300, 100% of 300, and then 10% of 300 makes 330. Everybody agree with me on that one? Maybe not the way you would write it, but do you agree that that's still correct? Okay. What about this? How have I changed it? If I put it into a decimal, I said 100% is one whole. One whole of 300 is 300, and 0.10 or 10, I should say, 1/10 of 300 is 30. Okay, that makes sense, right? So, 7th grade math, basically, 7th grade math is usually something like this. If you have, let's see, if you have a purse that costs $100, pretty expensive purse, right? And you want to discount it, by 10%. I want a discount of 10%. All right, most of you should be able to do that in your head. $90. You would take $10 off of it. But what if I had a number like this? What if I had $793 and I wanted a discount of 25%? How would you do that in a calculator? Okay, most of you would say 793 and you'd multiply that by 0.25. Correct? What would you get? 25% of it? Nope, can't be. Because 800. Yeah, give me a second. Okay, I heard 500 something. I knew that was wrong because 800. That's 198 sounds right because I know half of 800 is 4 and half of that is 2. So I knew the other one was more reasonable. So you guys said 190. What? 0.45 or 40? That's more than half off, so what do you have to do now? Subtract it. So I have to take the 793 and I have to subtract 198.50. Correct? That's an extra step. When I'm in the store, I don't want to do all that. So here's what you would do. Instead of multiplying 793 by 0.25, couldn't I multiply 793 by 0.75? Correct? That's just like saying 793 times 1 minus the 25%. Correct? Oh, is that how you got it? Yeah. Did you guys hear that, that's how he got that, was by multiplying? He gave me the answer before the discount, is what he did. Yeah. Okay. So, When I go back to this, does this make more sense now? Why I'd multiply the 300 by, let's do this. The next step here, my pretty little, let's do this. I'm just going to cover them up. So my next step would be to write it like this. 300 times 1.10 equals 330. Do you all agree with that? I'm increasing it by 10%, so it's going to be 1.1. If I increased it by 20%, it would be 1.2. So you don't have to do the math and then add. It's all done in one calculation, which works better when you don't have nice pretty numbers like 300, which guess what? We're not going to have nice pretty numbers like 300 that we can do in our head. Okay, so I'm going to take it one step more now. And when I do this, all right, so I want a 10% increase per year for 3 years. So I'm going to set this up as 300 times 1 plus for 3 years. Okay? Here's the equation. And let's talk about which each is. So here's the equation that I'm using. If I want to know for a certain amount of time, I would start with my initial amount of 300. If you want. Okay, so notice this is an exponential function. You've already talked about all of this stuff. This is an exponential function of 1.1. We can put 1.10 if you want to, if that's just a better visual, right? Where my base is 1.10. Which is an increasing function because it's greater than 1, right? It has a stretch of 300. Does that make sense? It has a stretch of 300 because we're not going to start at 0, 1. We're going to start off with 300 emojis. So if you were to graph it, it would start at 0, 300. Make sense? And then the T is how many years it's going to grow. All right. So here again, how many years will it take for there to be 900 emojis? If I want to know how many years it's going to take for it to be, I want to know after how much time are there going to be 900 emojis. Now here's the important part right here that I was talking about earlier. So I can actually solve this, but it's going to take logarithms. We're not going to do logarithms yet, right? We're just doing exponential functions. Because this is the way I would go, and I don't get freaked out, this is the way this would go. I would divide both sides by 300, and I get 3 equals 1.10 to the T. So does anybody know when you take 1.10 and put it to an exponent, you get 3? Yeah, any exponent. 1.10 to the 1, does that give me a 3? 1.10 to the 2. Is that going to get me a 3? 1 to the 2 is 1, right? What about 1.10 to the 3? Is that going to get me a 3? The answer is going to be no, 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 right? It's going to be some decimal. It's going to be, well, let's put it in a calculator and see. See how close you can get. 1.10 to what makes 3? Amadeus says he's convinced he's going to get it. All right, let's explore. Got ImageMate here. Can't really see it. Can we see it now? Maybe if I turn this off. My hands did look back, huh? Why? How is that racist? Okay, we can see it. Can you kind of see it now? Yes, sir. You think it's like, okay. So let's do, I'm going to do a parenthesis, and I'm going to do 1.1, and end parenthesis. I'm going to use that little caret symbol. Can you guys see it on there? Better? Can you see it now? Shut both lights off. Yeah, you can? Okay. So 1.12 that you think it's 11?
Yeah, like 11.6.
Give it a second.
Try 11.6. Yeah, 11.6. I mean, yeah, 11.6. Try to go to the right of this one. Move to the right of it. Yeah, there you go. That's good.
Okay, we're going to try to the 11.6. I think that's as close as we're going to get. Okay? So what that's saying is, it would take, in time, it would take 11.6 years, or no, 11 points, we were talking months, so it would take 11.6 months. Why am I putting 16? It would take 11.6 months to get this number. If I started, can I get you guys to quiet down, please? It would take 11.6 months if I started with 300 emojis. They increased by 10% every month, and I wanted to get a total of 900 emojis. Does that make sense where all those numbers are coming from? Kind of. Let's work with them a little bit. So, here, A is my initial amount, or my initial amount. That's what I'm starting with. Right now, we've been talking about exponential functions, and you guys start with a 1, because it's 0, 1, because that's the parent graph. Sometimes we talk about a stretch. It could start at 0, 3. That means the initial amount is 3. Then R is going to be my rate. That's my rate of increase. And T is going to be the time. All right, so now that we've talked about growth, what do you think decay is going to look like? It's going to be exactly the same formula, only it's going to be a minus sign. Do you see why I don't think I need to do 2 lessons on it? Like, one of them is positive sign and one of them is a negative sign. So I think now I have that Desmos activity for you guys to hang out with. So yours would be period 6. So why don't you get on Desmos and let's start talking about it in real life. Okay, so I'm going to go into Desmos. So I have 28 students in there. 3, 2, 1. Let's see some of the comments we're getting. We're getting 1.1, 1 plus 0.10 to the 2,000. Does that seem reasonable? There shouldn't be 2,000 on time. What about this one? 3 times, this one looks good. No, this one looks good, right? What about this one? That one's wrong. Are we seeing where we should be changing these? To the T. It's H2QNJZ. I'll write it up here. H2Q, and then space, NJZ. All right, let's see how you guys are doing on the graph. You type it in, and it graphs it. You have to put f of t equals. If you put f of x, it better be to the x power. If you put f of t, then it's to the t power. I can overlay, and we can see how many of us are on the same page. Most of you have it correct. So I'm going to let you guys work for about 5 more minutes, and then we'll go through the screens together. So which screen, Christian, which screen are you on? Okay, so on the third one, if you're trying to see, let's go to student. If you're trying to see on the third one, if this is the graph, oh, you were here on this one. So if you go on this one, if you go back to the second one, and let's put in the function, I can say f of t equals 3, parenthesis, what was it, 1.10 to the t. When I put that in, I can actually move my graph up to, what did it say, after $30. If I go over and I touch the graph there, do you guys see that it'll show me my x and my y? You can go up and down. That's called tracing the graph. So if I want to go up to 30, that would be, let's see, almost, 30 would be 24.17, or a little bit less than that. Yeah. That's how much time it would take to get to 30. So that's just a feature of Desmos that it's important that you know about. That you can solve for things by dragging along this graph here. When we did it, there's another way to do it. I could put in f of t equals, f of t equals 30. Isn't that going to give me a horizontal line? Then you can see exactly where they intersect. How cool is that? Right? That's how we would have done it when we were graphing them on our own, right? Solving an exponential function. So that's the most accurate way to do it. Okay, I think it's time for us to let's take a break. I want to just go through these slides really quick. So the student, the first one said to graph it. The third one said, what if you had, find the values. That was what we just found. Then this one says at the same time, Tony bought the baseball, it's spelled wrong. He also bought a signed card for $125. Experts estimated that the value increased by 20%. So you had to, it'll take the same amount of years? About, pretty close. Let's go through what you guys did. About 23 years. Then it says, how long would it take before the two investments would have the same value? So you had to find where they intersected. That was after about 10 years. We'll overlay it. So the first one I know is the one where it started with $3 because it's more. The initial amount is more, it's at 0.3. And the second one's at 1.25. So I know the orange one is the second function, and the red one's the first one. And then finally, what would be the total value of Tony's investment when the amount of the two investments have the same value? So I could go back and see how much, they're both around the same amount, right? Which is how much money? 7.5? So about 15 bucks together?
Oh, you went together?
Together, how much would the total investment be? Okay, guys, well-deserved break. Go.